Hello, everyone, and thank you for joining me here today as part of the 2021 Airport Planning, Design, and Construction Symposium. My name is Alec Cusick. I am a technical services engineer with Owens Corning, and I'm very excited to discuss our key topic for today, which will be general design considerations for insulating chilled water systems within airports. Starting off, I'd like to just give a brief introduction about myself. As I mentioned previously, my name is Alec Cusick. I'm a technical services engineer within the insulation business at Owens Corning. I hold a Bachelor of Science in Mechanical Engineering from the University of Toledo, and I'm a certified energy appraiser through the National Insulation Association. I'm also an ITC certified infrared level 1 thermographer and currently serve on multiple technical committees within industry organizations such as ASHRAE and the National Insulation Association. For those that may not be familiar, Owens Corning is a global industrial and building materials leader with 3 integrated businesses dedicated to the manufacture and advancement of insulation, roofing, and fiberglass composite materials. We have over 19,000 employees that operate in facilities across 33 different countries around the globe, and we're very proud to have been a member of the Fortune 500 company list for 66 consecutive years. With that being said, we'll go ahead and move right on into our main topic for today, which will be around chilled water systems within airport projects. Specifically, we'll start off discussing common challenges that one may face when designing around them. Now, it can certainly go without saying during an event like this, but airports are complex facilities with many challenging components and obstacles to design around. Chilled water lines within the HVAC commercial cooling systems are certainly no exception, and the insulation systems that are installed on them are a common area where reinstallation after initial construction may be required due to unanticipated system failures. Now, when we talk about chilled water systems, there's typically going to be a temperature range that we're referring to. This could be down towards 36 degrees Fahrenheit for your chilled water supply lines, all the way up to 50 or 55 degrees Fahrenheit for your chilled water return lines. If you've ever had a cold beverage out on a hot summer's day on a patio, you're already familiar with the phenomenon we're going to be talking about extensively here today, and that is condensation and moisture buildup all along that cold pipe surface. And this condensation can bring about a variety of challenges for the insulation system on that cold pipe. We're going to be talking today about strong vapor drive into and onto that cold pipe surface underneath the insulation, and that'll bring about an emphasis on the performance of the insulation system's vapor barrier. If that vapor barrier were to become compromised, the system would be subject to failure and could bring about a variety of issues. These issues may become immediately apparent, or in some cases, they may remain hidden for months or even years, waiting to be discovered down the road. Here we can see some of the most common examples of those issues typically found on failed chilled water insulation systems. They include dripping water causing slip and other safety hazards, the formation of mold and mildew, obviously a problem for indoor air quality, the corrosion of the metal pipe or other nearby equipment, as well as increased operating costs due to the loss of insulation efficiency. In many cases, the most immediately noticeable symptom of a failed insulation system on a chilled water line may in fact just be the presence of dripping water from the system itself. If water vapor is allowed to penetrate the vapor barrier of the insulation and condense on that cold pipe, it can build up to the point where it then re-escapes the insulation and drips down below to whatever happens to be underneath. If that's a floor, it then poses a slipping hazard for any nearby personnel. If that's a ceiling tile, it can cause unpleasant staining and other unsightly features that no one would want. And if there's equipment nearby that the water could drip onto, it could cause corrosion concerns for whatever that water comes in contact with. Another potential consequence of a failed insulation system on a chilled water line involves the formation of mold and mildew. Mold and mildew can grow in the presence of a food source as well as moisture. While I will mention that most insulation materials don't inherently provide a food source for mold to grow off of, most of the time the food source is introduced to the system after the fact. That could be something as simple as dust, debris, nearby floating skin cells, or other byproducts of the natural environment. Once moisture is introduced to the system, then you're at risk for the formation of mold and mildew to grow, posing an immediate indoor air quality concern for those around. Mold has been linked to many symptoms such as chronic fatigue, headaches, asthma attacks, and other lung illnesses. And toxic mold is the focus of a growing number of legal cases across the country. And the design decisions that lead to the formation of mold in commercial buildings is becoming a topic under much more scrutiny in recent years. Another byproduct of introducing moisture underneath your insulation system involves the potential for corrosion under insulation, or CUI, to occur. Some key ingredients for the corrosion of carbon steel include the presence of oxygen as well as liquid moisture. Oxygen is almost always readily available, whether it be from the air or dissolved in water itself. So once condensation takes place and liquid moisture becomes readily available, you do become at risk for corrosion to begin occurring. Corrosion can damage the outside of the pipes over the span of multiple years and can remain hidden and out of sight until it's well too late, in the most catastrophic instances, resulting in failure of your entire piping system in general. One more consequence of excessive condensation taking place within your insulation involves the loss of that insulation's efficiency. If the wrong insulation material is chosen, it actually can absorb and retain any moisture from condensation occurring. It's widely known in the industry that insulation becomes much less effective when it's allowed to become saturated with water. This can lead to thermal bridging, allowing more heat gain back into your chilled water supply lines, which will lead to energy losses and increased costs, requiring more energy to cool those pipes back down to that 40-degree operating temperature. This also leads to a loss of process control. Warmer supply lines will lead to a diminished cooling effect in the commercial building as a whole. And this also puts extra strain on your equipment, putting added stress on the chillers in order to reduce the temperature of that chilled water back down to the operating temp it needed to be at. Now that we've identified some of the most common issues associated with chilled water insulation failures, let's talk about some key considerations that can be made during the design phase of your system. I'd like to start off just by covering some key terminology that we will be discussing. Humidity is the concentration of water vapor present in any given airspace. Relative humidity is a percentage ratio that compares the actual amount of moisture in the air versus the amount that it could hold at a given temperature. Moving on, vapor pressure is the pressure at which water, both liquid and vapor, will exist in equilibrium. When the air temperature of a given space is lowered, this equilibrium is disturbed, and liquid water will condense as dew until equilibrium is achieved. And finally, the dew point is the temperature at which condensation will begin, and is a product of both temperature and relative humidity. When air cools to its dew point through contact with a surface that is colder than the air, water will condense onto said surface. One can view the topic of vapor pressure similar to that of normal pressure, and that is, vapor will always move from areas of high pressure to low pressure. Or you can think of it as moving from warm air to cold air, or in this case, towards a cold surface of a chilled water pipe. An insulation system with a compromised vapor barrier can allow this moisture in the air to move towards that cold pipe where it can then condense into liquid moisture. This insulation system can become compromised due to initial poor installation or damage that happens after the fact, whether that be from maintenance activities or typical pedestrian traffic that happens to be in the area. When determining the right insulation material for your chilled water system, one property you may want to consider is the permeability of that insulation material. Permeability is the tendency of a material to allow liquids or gases to pass through it. Permeable insulations rely solely on the performance of an external vapor barrier to keep water vapor out of a system. If that vapor barrier becomes compromised, permeable insulations can allow water vapor to move towards the cold pipe where it may condense along the surface. This condensed water can then be absorbed and retained into the insulation, which can compromise the K value, leading to lower external surface temperatures of the insulation. And you end up with a situation where you not only have condensation taking place on the chilled water pipe, but potentially on the external facing of the insulation itself. As you can see on the right, Closed cell insulations typically tend to have much lower water vapor permeability values than open cell and granular type insulations. I mentioned it briefly just there, but surface temperature of your insulation actually plays a pivotal role in proper condensation control as well. Proper insulation thickness is necessary to prevent surface condensation or sweating from occurring. Our goal should always be to ensure that the insulation surface temperature is greater than the surrounding air's dew point. Below you can see we have a chilled water pipe of 40 degrees Fahrenheit with ambient air of 80 degrees and relative humidity of 75%, giving us a dew point of 71.3 degrees. In this example, we make sure to use enough insulation thickness to achieve a surface temperature of 74 degrees, safely preventing surface condensation from occurring on our insulation. One thing I'd like to mention is that even in this scenario, there exists a point within the insulation thickness where the temperature falls to the dew point. However, as long as the system's vapor barrier remains intact, water vapor will not be able to penetrate to the point where it can freely condense. Within the industry, there exists many different standards from different organizations to help aid in the design of commercial insulation systems. One such standard is ASHRAE 90.1, the energy standard for buildings except low-rise residential buildings. This standard is commonly referenced in determining thickness requirements for chilled water lines. However, it should be noted that this standard is built around energy conservation, not condensation control. In reality, necessary insulation thickness should be calculated for each set of parameters and ambient conditions that's unique to your system. Another piece to consider when designing your chilled water system is the geographic location of your project. Different parts of the country will be subject to different temperatures and relative humidity, resulting in different vapor pressures. Here we have a rough illustration of the annual mean maximum dew point temperatures that various parts of the country typically experience. Condensation becomes a critical concern and a more likely problem to encounter in high humidity environments where there exists a much higher vapor drive from the ambient air towards a cold pipe surface. As a quick note, I'd like to point out that this map shows the average max dew point, but does not showcase extreme conditions that individual locations may experience. Of course, there exist multiple important but less obvious considerations that can often contribute to system failure. For indoor locations, you'll want to consider the environment and any additional risk factors that could contribute to increased humidity exposure. If the integrity of the building envelope is less than ideal, one may need to account for non-conditioned high humidity air coming into contact with chilled water systems. In an airport, this may occur at frequently opening doors, terminal gates, or conveyor openings within baggage claim areas. Another risk factor is whether or not a given building will be subject to what's referred to as idle building syndrome. If a commercial building is designed to be unoccupied at times, they may choose to shut down the air handlers of the HVAC system. However, the chillers and chilled water pipes are often required to remain operational. This combination of unconditioned, high humidity ambient air along with the same chilled pipe surfaces can create a prime environment for condensation to occur. In any scenario, you'll want to consider your specific environment and always design around worst case conditions for your system. Similar to indoor environments, outdoor chilled water systems may be subject to additional risk factors that need be considered. It is imperative to ensure any materials subject to direct sunlight have adequate UV resistance. Seasonal extremes in temperature and humidity will also need to be determined and taken into account. If in a location where exposure to jet fuel or jet fuel fumes is likely, chemical resistance to such materials may prove critical. Other important questions to ask include, will your material withstand burrowing activities of any local rodents or vermin? For direct burial systems, will materials withstand the compression load of soil backfill? If in high traffic areas, will materials withstand mechanical damage from pedestrian traffic or simply from the elements? Once again, the worst case conditions for your specific system should be determined and designed around. Another design consideration of your insulation system that should not be ignored involves the emissivity of the outermost jacketing to be used. Emissivity is the relative effectiveness of a surface to emit and absorb heat by radiation. It is expressed as a ratio between 0 and 1 and is most relevant to the outermost jacketing to be used on an insulation system. The higher the emissivity, the more heat transfer will occur between the material and its environment via radiation. When considering chilled water pipes in warm environments, low emissivity jacketing materials, such as aluminum and steel, will absorb less heat from their surroundings via radiation, which will result in a lower jacketing surface temperature. Conversely, high emissivity jacketing materials, such as PVC and ASJ, will absorb more heat from their surroundings, yielding an overall higher surface temperature for the same system. Here we can look at exactly how this effect comes into play in our design considerations. In our example, we have two 8-inch chilled water pipes operating at 40 degrees Fahrenheit, each insulated with an unnamed Type X insulation. There's no wind, and the ambient air is 90 degrees with 80% relative humidity, giving us a dew point of 83 degrees F. When covering our insulation with brand new aluminum jacketing, the surface temperature we get is 81.9 degrees. This is less than the dew point of the surrounding air and becomes an immediate concern for surface condensation on the jacketing to take place. However, when we take the same system and cover it with our PVC jacketing, more heat from the environment is allowed to transfer into the jacket surface, giving us a surface temperature of 86.7 degrees F, safely above the dew point where surface condensation will become an issue. As we've now learned, there are multiple factors that go into designing a successful insulation system for your chilled water applications. As a recap, when designing your system, you'll want to always determine the worst case conditions of your environment and plan accordingly. This includes the max temperature and relative humidity to be expected, as well as any indoor-outdoor complications that may be applicable. You'll want to be sure to calculate the thickness necessary to prevent surface condensation, taking into account the emissivity of the jacketing that will be used. And finally, be sure to allocate adequate spacing between and around pipes for the insulation to be installed. When selecting an insulation material for a high-risk environment, consider a material that is closed cell and non-absorbent, with a low to zero water vapor permeability rating. It should be durable enough to tolerate its environment and have a compressive strength to withstand any weight that will come to rest against it, especially for direct burial and pipe support applications. And finally, proper installation and inspection should be carried out during construction to ensure the system is properly installed and sealed against moisture intrusion. Well, now that we've come this far, I'd like to take a moment to discuss one solution in particular that may be considered for your chilled water insulation systems, and that is cellular glass insulation, a zero permeability approach. Starting off, for those that may not be familiar, what is foam glass cellular glass insulation? Foam glass insulation is a lightweight, rigid material composed of millions of completely sealed glass cells. Its closed cell structure and inorganic nature lend to unique properties amongst insulation materials within the industry. Foam glass is completely impermeable with a water vapor permeability rating of 0. It does not require the use of an external vapor barrier to achieve this, as the insulation itself acts as its own vapor barrier. It also boasts a relatively high compressive strength when compared to other insulation materials in the industry, making it suitable for direct buried and pipe support applications. It's also very dimensionally stable, having a thermal expansion coefficient similar to that of carbon steel, making it suitable for wide temperature cycling applications. Being 100% inorganic and made of glass, foam glass is non-combustible and does not give off dangerous gases in the event of a fire, making it suitable for fire protection and fire stop applications. It also is resistant to the nesting activities of common vermin and rodents that may be found in an area, and is chemically resistant in a similar fashion to many typical glass beakers you may expect in a laboratory. Finally, it's easy to cut and can be fabricated in the field or prefabricated to many different shapes and configurations prior to arriving on a job site. And finally, to wrap things up for today, I'd just like to cover some technical services that we as Owens Corning offer to those that we partner with to help you with your insulation system needs. Here with Foam Glass at Owens Corning, we maintain over 125 different commercial and industrial insulation system guide specifications. These can be used as a guide for engineers, specifiers, contractors, and facility owners for the design, installation, and maintenance activities of their insulation systems. They include products, detailed drawings, and installation guidelines for various applications. And in addition, we frequently review client specifications and are happy to provide advice to our clients to improve and advise on their specification needs. Here's an example of one of our detailed drawings that we offer, specifically for our chilled water system. We generate drawings like these regularly to help bridge the gap between specification and field installation, and to increase the confidence level that proper application techniques are being utilized on site. We maintain and utilize a full suite of proprietary thermal calculation software to help aid in the design for those who specify our insulation systems. If you have questions as to what insulation thickness or jacketing material to use in order to achieve a certain surface temperature, if you're curious about cost savings potential, or have general questions about process control, we'd be happy to assist with a thermal calculation report tailored to your specific system. We also provide on-site support around process improvements and energy savings. We have multiple certified thermographers on staff, myself included. We can arrive on site to perform infrared inspection surveys and conduct heat flow measurement and analysis. We can then issue a current insulation condition report, evaluate energy losses and savings potential, and provide advice on insulation system improvements to consider. We are seen as the industry leader in education, training, and startup support. We hold frequent training sessions that allow us to build relationships with our customers through shared experiences. These allow engineers and specifiers to become more familiar with our systems and allow contractors to better understand how to effectively install them in order to achieve the best performing system possible. Here you can see one of our global training centers located in Houston, Texas, where we frequently host these training opportunities. Please reach out to us with any interest on how we can collaborate with you and your team. Finally, Owens Corning offers a dynamic portfolio of insulation products to be used in a wide range of commercial building applications. Between cellular glass, fiberglass, mineral wool, and extruded polystyrene, we look forward to working with you to find the best solution for your application. If there are any questions on any of the topics discussed here today or about insulation systems in general, feel free to reach out. My personal email address can be seen down below, or you can reach out directly to our technical services and training team, again with phone number and email listed. We'd be happy to work with you on whatever your needs may be. I'd like to once again thank you on behalf of Owens Corning for your time here today, and please enjoy the rest of your day.